Hi, so this is just going to be a run through of the presentation I did for my psychology department's internal postgraduate conference. So I'm recording this and putting it up on my blog because some people who missed the talk were interested in seeing it, and just in case that isn't flattery, I'm going to pop it on here. And the blog's also going to cover how I narrated it and how easy it is to do this in PowerPoint if you also want to do this for your blog. And just so you know, I won the second prize for the People's Choice presentation, so if you want to take this as an example of at least a decent presentation, then feel free to do so, because at least some other PhDs thought I did a pretty good job. Okay. Hi, my name is Saskia, and I'm going to be talking about Likert scales and whether they are fit for purpose. So to start with, I'm going to talk a bit about my academic background because I think that's pretty relevant to this talk, and I'm going to move on to what Likert scales are trying to do, and finally I'm going to try and convince people to abandon Likert scales, and that part of the talk is going to get a little meta because I'm really talking about hypothetically what I'm going to do during my PhD. So I'm a statistician, I have a statistics degree, but I'm working in a psychology department, and that means that this sort of presentation is actually pretty crucial for my PhD because my ability to communicate statistics and convince psychologists to do things differently is really central to my work. It's almost equal to the fact that I have to, develop methods and things like that, which is why I chose this topic for my talk. So the first question is, what are Likert scales trying to do? Because you can't really critique something if you don't understand what its purpose is. So to put it simply, if you have a person and you try to measure their height, that's relatively easy. You just need some kind of physical measuring device, and bam, we've got a ruler here that can do that. But in psychology, obviously we often want to measure unobservable traits, attitudes, personalities, things that are much harder to measure because we can't actually use a physical measurement tool. So our goal is to try and make rulers for these latent variables, and that's a goal that Likert scales are trying to accomplish as well. So as an example, I'm going to go through the cat lover scale, which is a completely made up scale, which we're going to try and construct now. So if you wanted to know how much somebody loved cats, you might ask them what they think about cats. And to try and keep it standardized in some way, we're going to give them only 3 response options. So you think cats are rubbish, cats are alright, and cats are amazing, basically. And you'll notice that these are ordered responses because cats are okay is obviously the middle option compared to the other 2. So they have a natural order, and that means it's an ordinal response. So we want to go from their answer to some continuous scale. So here we have our cat lover scale. You'll notice that if you really like cats, that's indicated by the happy cats, that's our higher score. And then if you don't like cats, you're down there making grumpy cat grumpy in the lower end of the scale. So we might have some intuition that if you think cats are the best, you're somewhere near the top of the scale. Now, of course, we don't know exactly where you are on the scale because we can't see this ruler. This ruler is just, we assume there is some kind of scale there, but we can't actually see it. So we don't know how these 2 things link together. And the point is, we're trying to link the answer to the scale in some way. So we can place the person who answered that onto the scale. So to improve the estimate, you might want to do something like repeated measurements, such as if you're trying to measure someone's height, you might measure their height 3 different times. You might measure it 3 different times in a row, or 3 different times at different times of day, depending on what kind of area you're trying to get rid of, and take an average measurement. So to do that, we'd ask them multiple questions. So in addition to asking them the general what do you think about cats, we could ask them if they have a cat, assuming that if you have a cat, you're more likely to like cats. Ask them if they're scared of cats, which we assume has a negative relationship to our scale, because we're assuming that someone who's scared of cats doesn't like them very much, basically. And then to make a Likert scale, you would change these into statements. And sort of the main motivation for this, I think, is that it allows you to have sort of standardized responses. So you know that if someone has a positive cat statement and you just give them agree, neither, and disagree, that basically covers the responses we saw in the first question to I think cats are great, and they sort of, so it sort of also applies to do you, to I own / want to own a pet cat as well. So the point is that this response is relevant to all of the statements, whereas you might not be able to standardize responses to a set of questions. And then we know that if someone agrees to a positive cat statement, they're on the higher end of the scale, indicated by happy cat, and if they disagree with it, they're on the lower end of the scale, indicated by grumpy cat. So the I am scared of cats statement would be sort of the other way around. Grumpy cat would be agree and happy cat would be disagree. So to calculate your cat lover score, we now need to give these some sort of numerical value. So in general what we do is we use integer values that are sort of equally spaced. So agree gets a score of 1, neither 0, and disagree -1 for a positive statement. And you notice the third statement being negatively associated with the cat lover score gets reverse scored. And that's just because it's sort of we're saying it's sort of equivalent to saying you disagree with the first statement if you agree with the last statement. So let's say somebody answers the question and they're kind of respectful of cats, but they're a bit fearful. So they think cats are great, but they don't really want to be around them or own one, and they're kind of scared of them. And then this person would get a score of -1 because we simply add all the scores together. And this is still like a repeated measurement. The only reason you don't average them is that because everyone answers the same number of questions, all you would be doing is dividing everyone's answer by the same number. So divide everyone's answer by 3. So basically, there's no point to dividing it by 3 because they sort of would still relate in the same way, and that's why you don't bother and you take a sum. But it's basically it's the same purpose as taking an average, just in this case, taking an average doesn't really matter. Interestingly enough, our Likert scale construction, while we've used these scores, has actually defined a ruler. So we've said that it has to be between -3 and 3. And also we've said that you can only have integer values, and that's because we've used integers, and the highest score you can get on each one is 1, and the lowest score is -1. So it can only be integers between -3 and 3. So now we can very precisely place our example previously onto this ruler. So there we go, we've defined a ruler that covers the underlying latent variable. So this is basically supposed to be a proxy for the latent variable ruler, which notably we still can't observe, and we still don't know exactly how this ruler relates to the invisible ruler, the unobservable ruler. But on the whole, you could say, job done. Unfortunately, there are some logical problems with this method of scoring. Basically, you make some unwarranted assumptions. So you're assuming that all the items relate to the latent variable in the same way. And it's important to remember that this is a mathematical assumption, and it's not in fact generally what a psychologist is doing, because if you were trying to do that, you would basically only expect to get really 3 scores. You'd expect everyone to get a score of 3, 0, or -1, because you'd expect them to answer their questions the same way each time. Similar to how if you measured somebody's height, you wouldn't expect them to get a really different measurement each time, and the only measurement you'd expect would be sort of random error. But in general, we kind of want the items to cover sort of different attitudes toward different specific attitudes towards the cat, or like whatever you're measuring. So the psychological assumption, as I've seen it described, is not relating to the mathematical assumption, which is quite strict, that you're making here, and that's one of the problems with the Likert scale procedure. You're also assuming that the distance between agree and neither and disagree is equal. Now in this 3 response case, you could probably make a stronger argument that that's true, but one of the main points is that if you look at something like item response theory, it can quite clearly show that different items can have different sort of psychological different distances or distances on the latent scale between these responses. So the items might not have the same distance, and it might not be equal distances between agree and neither and disagree. You'll also see that sometimes people have a forced choice response format where there isn't a neither option, and when you have, say, 5 responses and then you take out the neither option, to say that the difference between the end 2 responses is the same as the middle 2 responses doesn't really make a lot of sense, because you're also making the same assumption that the difference between the far two responses and say agree and neither in the middle is also the same. So you're kind of shooting yourself in the foot there. It's basically not possible for those to both be true, because once you take the neither out, even if it was equal before, you'd now sort of have double the distance in the middle, and that's also not something people take into account. So because the ordinal categories have unknown distances between them, which is basically a property of the data, you can't actually sum it. So this last part is invalid. You can't make this score, and because Likert scale scores then don't really have a data type, they're uninterpretable and cannot be analyzed statistically. And what that means is that while it is true you can analyze any numbers statistically, whatever numbers you want, it's uninterpretable because it's sort of like nonsense in, nonsense out. If you statistics can't be divorced from context, and the knowledge of what the data type is and where the data has come from is so very important to statistics, which is why I would say you can't analyze these statistically. That obviously is true, you can analyze any set of numbers statistically, you can code anything as numbers and analyze it using a method, but it's invalid in the sense that your answer means nothing. So the real question is whether I've convinced anybody yet that you shouldn't really be using Likert scales. And a key part of my thesis will be trying to make this case. I'm going to just move on to talking a bit about how I'm going to make the case. So really, you want to provide an alternative, and you might also want to use simulations and case studies to sort of prove to someone practically minded that there is a practical difference between Likert scale scores and a more principled method of finding scores on a latent variable. So my alternative is to model the items. For anyone interested, my specific model is the ordinal probit model, though I won't be going into any details here. So on the right here we've got my items, and let's say we want to have some independent variables that relate to our items. Now what you can do is have a latent variable in the middle, so the independent variables relate to the latent variable, which then relates to the items. So within this process of the model, you actually do end up estimating the latent variable scores, and the latent variable is involved in this process. And that, I think, is a key reason why this model could be useful in the Likert scale context. So my approach is a model with an ordinal response, and you have ordinal data because the item responses are ordinal. So that's good, they kind of match up. You end up estimating the latent variable score, which I hope can be a replacement for the Likert scale score. And also it's applicable to any Likert type items. These sort of ordinal methods you can use them on anything with an ordinal response. You can use them on a set of items that each have ordinal responses. Like, they don't necessarily have to be related, because to make a Likert scale you actually have to do quite a lot of statistical sort of analysis to make sure that they correlate well with each other and that they correlate well with the Likert scale score. But this approach will generalize to any situation where you have ordinal data, so that can be an advantage as well. Unfortunately, it's mathematically and computationally complex, particularly as in my case I'll be using Bayesian methods, but the whole point of my PhD from a statistical point of view is to make these methods sort of accessible. I'll probably end up making some kind of R package or something like that to help people use my method. So that's not, I don't think that's a big issue for this talk at least. However, my personal concern is that maybe the score estimates are not practically different to Likert scale scores, in which case it may be difficult to convince people to change their ways, as it were, because if there's no practical difference they might go back to using what is a simpler method. So in order to convince pragmatists, you could use a simulation, and in a simulation study you would generate typical data sets from some sort of data generating process, and you'd compare the general differences between the two methods. So you'd probably fit my model to them, and also just get Likert scale scores, and then see what the differences are, and how they relate to, in this case, you probably would have given each sort of imaginary participant a latent variable score, so you'd see how recoverable that is, and whether the Likert scales can sort of approximate that. So it's good because they provide evidence for average outcomes in typical situations. Of course, it's difficult to define a typical situation, and by average, I basically mean that in some sense, if you make 1,000 data sets from the same process, then you know that maybe 95% of the time my model works better. Then you could say that if your data fits into that sort of typical data generating process, then you can sort of think that like approximately 95% of the time my method will work better on your data as well. So that's what I mean by average. It's not really a strict definition because it depends on how you've generated your data. It can also be quite compelling because of the large number of data sets. A lot of people find simulation studies very persuasive. The only thing is, if you don't have the theoretical backing, I don't think they should be taken that seriously. But they persuade a lot of people, because it gives it a sort of objective feel, it's sort of a good test for your method. So like I said, defining typical data set can be difficult. And also because artificial, it may be unrealistic. Usually when you see a simulation study, there'll be like a whole bunch of caveats at the end about what they couldn't include. Often the data generating process is really simplified, and the question of whether it's too simplified is kind of an open question. It's hard to say. So that can be a bit of a problem. Additionally, you could use some case studies where you take a single existing data set and compare the two methods in detail. So it's like a simulation study, really, except that here you only have one case or maybe a couple of cases, and it's a real data set. So that's where the main advantage comes in. You have your real data, so no one can say it's not realistic because it's real. It is realistic. It's happened at least once. And more importantly, it provides a real opportunity for demonstration, to demonstrate your method, maybe to demonstrate how easy it is to use, and really do like a kind of how-to. So you may have presented theoretically the maths, the complicated model, in my case maybe priors and things like that, and people might be like, oh, I don't know how to do that. But the point is that if I've also provided some sort of standard way to do it, or an R package, I can then demonstrate how you would use it, and that makes it far more accessible and easy for people to use. Of course, you want it to be as representative as possible, kind of the same problem as a simulation. And you kind of don't want to be accused of cherry picking, because that would be a disadvantage. Of course, the difficulty is you might not be able to find one, and to be fair, what I mean by find one is more that if you were gonna use it as evidence that your method was better, you'd want a really clear-cut case where your method was better, or to be able to show that in a specific situation your method is almost always better. So the problem is you basically might not be able to show that your method is way better, but you can still demonstrate how your method works. Now, for the same reason that you might have to search a bit to find one that supports your point and, is applicable, people are probably unlikely to have their minds changed by a case study because, you probably did pick it to demonstrate your method well. So from that perspective, they might think, you cherry picked it because you probably did. You try to minimize that, but you probably did to some extent. So really you want to use these two methods together, as well as having some kind of theoretical justification, and that really gives you a nice body of evidence to convince people. So at this point in my talk in the department, I obviously had questions, and I got a tip from a fellow PhD that you should have your last slide have a little summary of your talk, because it can remind people of their questions, and it can, help people to remember what you said. Actually, to just add to this at the end, my friend is at Bristol doing a sort of physics PhD. His name's Keith Alexander, and he gave me some useful tips, which I'll relate more in the blog. But yeah, basically this was one of his tips. And another one was that often you get advice to minimize your text. And he made the point that that sort of only works if you're a very engaging speaker, and when you're starting out, it probably helps to have little bits of text on your slides, because when people sort of maybe drift off or lose interest or get distracted, they can then anchor themselves back on your uh, presentation. So that's kind of important. I'd like to thank him for his advice, which I really think did help me get my second prize. So also thanks to everyone at Cardiff University's psychology department for voting for me. That was really nice of you, and I hope that anyone watching this has learned a bit about Likert scales and why they're problematic, and also a little bit about got some ideas about how to do their own presentation, and I'll cover more about my tips for presentations under this video.